In this video, I want to go over the big picture of the process that you will be using when you have to work with Newton's second law. So, Newton's second law, I'm going to write it here. Net force is equal to dp over dt of the system. And assuming we're dealing with motion where the relativistic factor is roughly 1, then this will allow me to say that the net force is approximately equal to the mass times acceleration. Now, this physics principle relates net force, which describes interactions, and the acceleration, which is about the motion of the object. Now, what the steps that you will be following? Okay, of course you will be drawing a picture, coordinate system. You have to choose a coordinate system. And you will be drawing the system schema to show the interactions, the force diagram, but then you will find the net force. Okay, you will find the net force from all forces acting on the system. Okay. So, system schema, show the interactions, force diagram, force vectors, and then you will find the net force from all forces based on everything you know about the interactions of the system with the surroundings. And then what you will do, as I said, you have to make a choice for the coordinate system. Now, the one that we typically use in introductory physics, the Cartesian. Another one that we use in upper level physics classes, cylindrical. Now the Cartesian, you can do it 1D, 1 dimension, 2 dimensions, 3 dimensions. Cylindrical is but most often the most is 3 dimension cylindrical. If you only have 2 dimensions, you can make a note. This is 3D. This can go up to 3D. And if you only have 2 dimensions, you can do polar. This is 2 dimensions. So you will have to choose. Now there is another one, of course. We also have the spherical coordinate system, 3D. So you will have to choose a coordinate system. Now the thing is, and I have shown you this in a different video, in Newton's second law we have, okay, you found the net force from all forces. You're done with the left side. Now we have the mass and the acceleration. Mass is a number, and then we have the acceleration. The acceleration, the way that you will write the acceleration depends on your coordinate system. So once you decide what coordinate system you will use, this will determine what expression you will use for acceleration. For example, we know that in the Cartesian coordinate system, you will write the acceleration as the second derivative of x with respect to time times x hat plus the second derivative of y with respect to time y hat plus the second derivative of z with respect to time times z hat. Okay, this is the acceleration in the Cartesian coordinate system. Now, in the cylindrical coordinate system, the acceleration is going to look different. And in particular, Now, for this cylindrical coordinate system, different people, unfortunately, they use different notation, different symbols for the radial variable and the angle. Okay, don't get stuck on what symbol I use. It will be the second derivative of, say, s with respect to time minus s d phi dt squared and all of this is the s hat component plus s, the second derivative of phi with respect to time, plus 2 d, okay, this would be ds dt d phi dt, and this is the phi hat component, plus the second derivative of z with respect to time z hat. Okay, this is the acceleration. This is the expression for the acceleration in the cylindrical coordinate system. Fairly different from the one that we have in the Cartesian coordinate system. For spherical coordinates, it is even more complicated than the one I wrote in the cylindrical coordinate system. For polar coordinates, essentially what you have is simply the first two terms, the s hat and the phi hat of the cylindrical coordinates, because cylindrical is s, phi, and z. Polar is just s and phi. So here I'm using s, phi, and z. For polar, we're just using s and phi. And for spherical, we use r, theta, and phi. For Cartesian, it is x, y, and z. Okay. Now, the important thing, once you decide what the coordinate system will be, you need to copy and paste the expression for acceleration in Newton's second law. Okay, so what I want you to do, once you find the net force from all forces, that's gonna go here. Once you decide what the acceleration is for your coordinate system, that's gonna go here. And from then on, you will have to solve the equations, the differential equations that you get solve the differential equations to obtain the equations of motion. And I will talk about that. The goal, the predictive power of Newton's second law is that it allows us to predict the motion. If I know what the net force is, I can predict what the acceleration is, and if I know the initial position and initial velocity of my system with the acceleration, I can predict how my object will move. So the strength, if you want, or what I can get from Newton's second law are the equations of motion, how the object moves. Now, what the equations of motion, what this means depends on your coordinate system. If you use Cartesian coordinate system, then the equations that you need to get from Newton's second law are the following. What the acceleration in the x is as a function of time, what the acceleration in the y is as a function of time, what the acceleration in the z is as a function of time. You also need to get Vx as a function of time, Vy as a function of time, and Vz as a function of time. And also x as a function of time, y as a function of time, and z as a function of time. These are the equations of motion in the Cartesian. Once you have all of these equations for all of these quantities, these will be the equations of motion in the Cartesian coordinate system. Now, if you choose a different coordinate system, say the polar coordinate system, then you need to get the acceleration, the s component of acceleration as a function of time, and the phi component of acceleration also as a function of time. So in the cylindrical, you would need to have z as well. And then you would need to have the velocity, the s component of velocity as a function of time, v phi, and vz as a function of time, and then s as a function of time, phi, and z as a function of time. So you're going to have equations for all of these. That's what you're going to get from Newton's second law. Now, if you're only dealing with the polar coordinates, then you just have these 6. You don't have the z one. Now, this is in the most general case. If you have a problem that is where your system is only moving in the x direction, okay, in that case you will have no quantity of interest is going to be in the y or the z directions. You will only need to find ax, vx, and x because everything else is going to be 0. Similarly, if you have an object that is moving on a circle whose radius is constant and it's not changing z, then all of these are going to be 0, and all of these are going to be 0. You will only have to find the phi related quantities because that's the only variable that is changing from your coordinates. Okay, so this is the big picture of how you will be approaching Newton's second law problems. Find the net force from all forces and choose the expression for acceleration on the coordinate system that you have chosen. How will you do that? Look in the book and copy and paste the expression for acceleration for your coordinate system, and from then solve the differential equations to obtain the equations of motion. And depending on the problem, you're going to get different equations of motion. That's all.